So now I want to take a step back from this multiple hypothesis testing stuff we've been talking about and go back to a different way of looking at hypothesis testing to begin with. So remember in the classical framework, we kind of think about the p-value, which is like, if the null is true, what's the probability of getting like the data that we got or something larger, something like more in the direction of the alternative. And so really that's thinking a lot about if the null is true, right? Like if the null is true this, if the null is true that. And if we think about our 2x2 table, our old friend, right? We have the row where reality equals 0, the row where reality equals 1, and then columns for our decisions. And this corresponds to thinking about this top row, right? Where remember that we say null corresponds to reality 0. And so like the p-value idea is really thinking about this case where reality equals 0, this top row, right? And in this top row, we can make true negatives, or we can make false positives. And we think a lot about the false positive rate, which is like the probability of, if the null is true, what's the probability of making a wrong decision, right? Like this is one of these row-wise rates. And we talk a lot about the false positive rate, trying to like, keep that small. And we kind of said, oh, false positive rate is a p-value threshold. But what about the case where the alternative is true, right? We also have these other possibilities, right? False negative, true positive. And what if I care about the false negative rate? Well, the classical hypothesis testing framework doesn't really have a way of thinking about what happens if the alternative is true, right? Because remember, our alternatives are always like vague, right? We can't really specify probabilities under an alternative like the mean of the two groups is different. Like that doesn't really give us anything to go off of to like calculate a probability under. So what we're going to do is we're going to specify more specific, more detailed alternative hypotheses. Okay. We're going to say not just like, oh, the alternative is like the mean is different, or the difference between the means is, mean of the two groups is different, or the mean is greater than this amount. I'm going to say the difference in means between the two groups is like 3.5, or the mean of this is not just 0, it's like 7.9. So essentially what that corresponds to is fleshing out this bottom row of the table. So, we have I can go back to our picture where, we have this, which I always like to draw, which is, the distribution of the test statistic under the null, right? And like, this is kind of what we use to like calculate and think about our p-values. But now we're also going to draw a specific distribution for the alternative. So this is the same thing, distribution of the test statistic under the alternative. So now I'm getting a more concrete kind of, I'm saying, okay, I'm drawing a line in the sand and saying the alternative, like it's here. It's not just bigger, it's like actually here, right? Like maybe this is, I don't know, like the test statistic is 0. Maybe this is, the test statistic is 10, right? How you choose it kind of depends on what you think the alternative should be. There's definitely like, some art or some specific thing that goes into how you choose this. But, there you have some specific alternative hypothesis. And so, we can say, hey, if my test statistic is like here, then, the probability of the test statistic given the null, very small, right? This density is really small. Probability given the alternative, pretty high. So I should probably, favor the alternative if I get a test statistic here. And, if I get one that's like way over here, again, I should probably favor the null. And we can see there's kind of this like critical point where the densities are equal that, it's kind of like 50-50. But what if, I said part of the point of this was to like kind of think more about this false negative rate. What if I want my false negative rate to be really, really, really small, right? Like what if I really don't want to make any false negatives, which is kind of something that's like a little trickier to quantify in the classical setting. But here I can actually reason about that more, right? And the way I can do it is saying, well, maybe I'm okay with, if I have a point that's like over here, sure, the likelihood under the alternative is smaller, but it's not like that much smaller, so maybe I'm okay with it. But that's kind of hand wavy, right? I'd like to get a little more concrete and be able to specify, okay, if I want a false negative rate or I want a false positive rate of this, where should I draw the line, right? Where should I draw the line between picking one or the other? And so what we're going to do is we're going to calculate the ratio between the green distribution and the blue distribution. And this is going to be called the likelihood ratio. So for the particular test statistic we get, it's essentially just what is the probability of getting that test statistic given the alternative divided by the probability of the test statistic given the null is true, right? So essentially just saying, like, let's take the green, divide by the blue, right? And right here, you can see that, you know, that ratio is going to be 1. And then as I go out here, that ratio is going to be less than 1. And I go over here, ratio is going to be bigger than 1. And I'm going to compare that to some value. And the way I compute that value is by using the false positive rate or false negative rate that I want. And then I'm just going to plug in the test statistic I get. And you'll get more practice working with this on the homework as well. But this is essentially the Neyman-Pearson framework.